Yeah, everyone's going to miss the wetsuit stuff. Okay, there we go. Thank you, Polly.
Welcome, everybody. We are going to be talking about predicting time between events, survival analysis 3 ways. I'll give you a little bit of a spoiler. The 3 ways are old school, new school, and my school. My GIF is going to take a little, oh, okay, thanks.
Just letting you know.
We'll get there. Okay, so I thought you might want to start off by hearing a little bit about me. I don't know if you're familiar, but this is from Disney's 1951 Alice in Wonderland. I was obsessed with that caterpillar growing up. So I'm Andrea. Hello. I'm a senior data scientist at Warby Parker. If you're not familiar, Warby Parker is an international eyeglasses retailer. We kind of have a mix of a fleet of brick and mortar retail stores, as well as, a fully fledged e-commerce and mobile app business. At Warby Parker, I work on problems like enhancing product discoverability for customers, making it easier to find glasses that they would like, doing things like building recommendation engines. I also support experimentation on the website, and I am exploring how we can think about building customer segments. Prior to my time at Warby, I was with an ed tech company called BrainPop. BrainPop is a product that is sold to public schools. So it's something that a public school or a district would buy and provide to teachers to have in their classrooms. And at BrainPop, I worked on problems mostly with our sales team, our finance team. And I worked with those teams to understand how activities that sales members would take, activities like emails or cold calls or a demo, how those would relate to later conversions. And then before that, I'm an academic. So I got my PhD in cognitive science. I studied low-level perception for speech and faces, which is a really fancy way of saying I studied how we listen to speech and I studied how we look at faces. One more sort of housekeeping note before we jump in. There is code in this talk. This next piece of advice might sound a little bit counterintuitive. I don't really want you to worry about it too much. So really, I want you to not sort of focus on the details, really just kind of think about the high level. And as I said, I know that advice might be counterintuitive, but I think hopefully it'll make sense because my goal for today is for everyone in this room to leave with an understanding of the problem. I want to communicate the kinds of situations in which you would want to use survival analysis. Of course, I will tell you what survival analysis is. I want to communicate why it's really, really important not to treat censored observations as missing. I'm going to show you a couple of different R packages for implementing survival analysis. And then last, we're going to build an intuition for how survival analysis. So nowhere on that sort of list of topics that I want to cover did I say, really worry about low-level details about the code. Really, I would just say sort of focus on the high level. It's all on GitHub. I will share everything afterwards, and you can go back to it if you want. There's a whopping 3 lines of code that we're going to walk through in detail, and I will draw your attention to those. Okay, so predicting time between sign up and churn. Let's imagine that you work for a communication services provider, right? You work for Xfinity, you work for Verizon, you work for Waitsfield Telecom. A huge part of the business is going to be understanding renewals. So ideally, you want to understand how long you are going to be able to maintain customers for. You want to be able to understand customers who are going to renew, and you want to be able to understand customers who are going to cancel their contract or churn, right? So ideally, what you'd like to have is you'd like to be able to estimate the probability that someone is going to remain your customer. I'm going to be using a data set from Cattle throughout, but before we look at the details of that data set, I have some fake data here to illustrate a point. So here, what I'm plotting are some fake customers, and their sign-up dates are shown with the blue dots. So their sign-up dates are shown on the left side in blue, and their churn dates, their cancellation dates are shown in red on the right-hand side. So if we look through this fake data, let's start with customer Alice. So Alice signed up in 2019, and then she churned, she canceled her contract in 2020. And then let's look at the second row. So let's look at Bob. So Bob signed up in 2020, and then Bob canceled or churned in 2022. But if we look at the third row here, Charlie, you see that Charlie signed up in 2021, but we haven't observed Charlie churn yet. Charlie's still a customer. So we have not observed his event of interest yet, right? Charlie still has his contract. And the same thing is true for Dave. So Dave also, Dave signed up in 2022. Dave has not canceled or churned, right? We have not observed the events of interest for customers like Charlie and Dave. So Charlie and Dave are examples of censored observation. And censoring means that we know something about the individual's starting point, in this case, their sign-up date, but we don't know something about their ending point. We don't know about their cancellation or their churn date. And a very common response when dealing with censored data is to filter these observations out, right? So we're going to say, okay, I don't know what their cancellation date was. I don't know what their churn date was. I'm going to treat them as missing, but they are not missing. Indeed, we have partial information for them. And to simply sort of filter them out of analysis, an analysis, as we're going to see, is going to result in incorrect estimates. So I am showing here just like a little bit of dplyr code that shows how you might sort of construct a naive estimate of the probability that someone will stay your customer in the biomedical literature, right? You would say it's a survival probability. So I'm showing sort of a naive estimate of that survival probability, but these estimates are incorrect, right? So these estimates are basically, I'm saying 1 minus the total number of individuals who have churned, who have canceled, divided by the total N in the sample. And as we're going to see in a minute, this is going to really overestimate the survival probability. And this is actually a very common pitfall. And the reason that this is really a problem is because censored individuals only contribute information for part of the time, right? So basically, they only contribute information for as long as they are in the risk set. And then they need to fall out of the risk set, right? They basically need to fall out of the denominator. And if we ignore censoring, we have an incorrect denominator. So if we treat these individuals as part of the risk set, we're going to have an incorrect denominator, and these individuals are not really eligible to be part of the risk set for the entire time. Thankfully, and we run into censored data all the time. So there's lots of examples wherein data is censored. So the sort of hallmark example and the example after which sort of this set of techniques is made, survival analysis, comes from biomedicine, right? So we're predicting time from disease onset until death. But there's lots of other examples, right? So maybe you want to predict time from a machine part creation, so widget creation, to widget failure. Maybe you want to predict the time from a customer's first order until their second order, or in our case, maybe you want to predict the time from sign up to churn. So if you find yourself asking how long until, or has it happened yet, you are probably dealing with censored data. And it's worth calling out that these are all examples of right censored data, right? So these are all examples where we sort of know the starting point, but we don't know the ending point. That's not the only kind of censored data. There's other kinds of censoring, but I would say right censoring is the most. And thankfully, we have tools at our disposal to help us address censoring in our data. Survival analyses are a collection of tools that help us do just that. I'm going to focus on two very common methods today. So I'm going to focus on Kaplan-Meier estimates and Cox proportional hazards. So Kaplan-Meier estimates are used to estimate survival probabilities, and Cox proportional hazards are used to quantify effects between one or more covariates. Cox proportional hazards can also tell us the likelihood that an individual is going to experience the event of interest within a really small time period. Okay, So first off, before we start with a little bit of modeling, what does time to event data look like? Thankfully, this is really straightforward. You need two variables for time to event data. You need some variable of time. In this data set, time is called tenure, and this is tenure in months. As an aside, the units of the time variable don't matter. So you could have time in years, you could have time in months, you could have time in weeks, whatever. And then you need an event marker. And so in this case, an event 0 means the event has not been observed, and event 1 means the event has been observed. So event 1 means that the customer has churned, and event 0 means that that customer is censored. So given just these two variables, we can start to generate overall survival curves for the entire cohort. So I am using the survival package to do this. This is a pretty standard way to do this. In fact, I would say this is the old school way to do this. And in just a few lines of code, we can get estimates of survival probabilities. So the way that we interpret these survival probabilities is that these estimates in the estimate column represent the conditional probability of surviving beyond time t, given that an individual has survived to time t minus 1. So it's basically saying you're going to survive past month 4, as a for example, conditional that you have survived up to month 3. Right, so we would interpret this, I don't know if anybody can see, right, if I show the estimate right here, 0.928, we would interpret this as saying 92.8% of customers who survive to month 2 will survive to month 3, right? So conditional that you have survived to month 2, that's your likelihood of surviving to the next month. And then once we have those estimates, we can start to plot Kaplan-Meier curves. So again, the interpretation of this is the conditional probability of surviving beyond time t, given that the individual has survived to time t minus 1. So we would sort of interpret this as saying, about 70% of customers who survive to the 4-year mark will survive beyond that, conditional that they have survived to 3 years and 11. And I'll pause right here to see if you can see where I'm pulling that out of that graph, right? So at the 48-month mark, we're seeing it hit just about 70% on the y-axis, right? So we're sort of saying conditional that you've survived to 3 months and 11 years, we think 70% of folks will survive beyond. And you can see here that if we compare the Kaplan-Meier estimates to our naive estimate, you can see that these lines have diverged, right? You can see that our sort of initial naive estimate really was overestimating our survival probability. So in a minute, we are going to dig into the math of why this is true. But for now, the key takeaway is really that we have to address censored observations in time to event data, and we cannot just treat them as misses. So another thing that you can do with Kaplan-Meier curves is that we can stratify by a variable of interest. So there's a variable in this data set, there's other fun variables in here, but there's a variable in here that is called internet service type. So folks either have DSL or they have fiber optic, or maybe they don't have an internet service. And maybe you have some sort of intuition that survival probabilities would differ depending on the type of internet service that you have. So again, I am using the survival package, the old school sort of way of doing this, and I have made one little change. So I just, in the formula call, I am stratifying now by internet service. And now we are going to have each of those survival probabilities, but broken out for each internet service. And then when we go ahead and plot the curves, we can see, hey, yes, it does indeed look like survival probabilities differ by internet service type. So we can sort of see that maybe surprisingly, if you don't have internet, you sort of have the highest survival probability. DSL is kind of in the middle, and then fiber optic has has the lowest survival probability. And this was maybe a little bit surprising to me at first. I thought like, oh, okay, that's kind of interesting. But actually, if you think about it, you can kind of, maybe there's a story there. So, maybe if you're moving, if oh, I know. So the folks who don't have internet, there's other variables that show if they have like a phone plan. So most of the folks who don't have internet have a phone plan. If you move and your internet service provider is not available in your new location, maybe you have to switch, Verizon, Xfinity, whatever. But more likely than not, you're able to take your phone plan with you. So maybe there's a story there for folks who have, phone service are less likely, are more likely to remain customers, but folks who have fiber optic have lower survival probabilities. But I'm sort of basing what I'm saying here off of simply just like the height of the curves, right? So I'm just interpreting the plot. I'm basing what I'm saying here off the height of the curves. What if we wanted to quantify those effects, right? What if we wanted to say like, hey, well, how different is DSL from fiber optic, or how different is fiber optic from not having any internet service? This is where a Cox proportional hazards would be really helpful. So I am showing some syntax for how to execute the Cox proportional hazard. This is in the old school sort of classic way of doing this. So again, we are using the survival package, and I am printing the results of the model right in the console. And you can see there's a couple things that I want to draw your attention to. So number one, we have a coefficient, but we also have an exponentiated coefficient. So you'll see, right, we have the coef and the exponentiated coefficient columns. The other thing that I want to draw your attention to is that we have these for two, right? We only have two rows. So we have a row for internet service fiber optic, and then we have a row for internet service node. And that is because our defaulted to an alphabetical coding scheme, the reference is going to be DSL. Does that make sense? So it's basically, I didn't specify what the reference group was. So it's going to say, hey, well, DSL is first, it's alphabetical, DSL is my reference. So what these coefficients represent, the first row represents the comparison of DSL to fiber optic, and then the second row represents the comparison of DSL to no internet. Yes, we talked about the coefficient and the exponentiated coefficient. So there are more modern ways that we can execute this. So here I'm showing that exact same Cox proportional hazards, but instead what I'm showing you is I am showing you the censored package. And censored is a parsnip extension package. If you're not familiar with parsnip, parsnip is part of the tidy models ecosystem. And really what parsnip is setting out to do is standardize the way that you fit models. So if you use R, you have almost certainly encountered the problem that there are loads and, well, not the problem. There are loads and loads of different R packages. But what that also means is that there are loads of different ways to fit a model, right? There's loads of different ways to syntactically implement a model. There's loads of different ways to make predictions. There's loads of different ways that you will get an object back. So what tidy models is really seeking to do is sort of standardize how you specify that model. So while you might look at this implementation and you might think like, hey, Andrea, that's a little verbose, like that's a lot of lines of code. I just want to, fit a regression. And I would, agree with that assessment. Where I think tidy models really shine is the ability to toggle back and forth seamlessly between lots of different model types. So I'll give one quick example. If you wanted to switch this to a regularized regression, it would just be one line of code change in censored. But if you wanted to do that sort of outside of censored, you have to use the GlimNet package, and the GlimNet package doesn't have a formula interface. You have to do a model matrix. It just becomes a whole lot clunkier. So my heuristic, as sort of I think about it, if I were just like, oh, I'm going to run one quick Cox regression, I just want to, look at the relationship between this, these this one covariate, I'd probably start with the survival package. But if you're going to be toggling between lots of different model types, then maybe censored is the way you want to go. All right, so we saw an old school way of doing this, and we saw a new school way of doing this, but we have to talk about what exactly those coefficients represent. So what exactly is a hazard of churning? So the output of that Cox regression, we talked about, we have both the coefficient and we have the exponentiated coefficient. And we're really interested in a couple of things when we have that Cox regression. So first, we're interested in the hazard, and the hazard represents the probability that an individual is going to, that we're going to experience the event of interest at time t plus 1 if that customer has not churned as of time t. So it's this sort of instantaneous likelihood, predicting the likelihood that you're going to observe that event in the next instant. So basically the next sort of unit of time, conditional that that event has not been observed yet. And then the hazard ratio, the other thing that we're often interested in, and the hazard ratio is the ratio of hazards between any two groups at a particular time. So we saw the hazard ratio in the outputs that we were just looking at. So the hazard ratio is calculated by exponentiating that coefficient, which is why it was in that output. So essentially, if we have a coefficient that is less than 1, right, when we exponentiate it, the hazard ratio will also be less than 1. And then we interpret that as a reduced risk of churn. So the opposite of that, the converse, is that if we have a coefficient that is greater than 0, the hazard ratio is going to be greater than 1, and that is going to map onto an increased risk. So if we go back to our outputs, we can see, right, so we're going, our hazard ratios are in the second column, and we can see the hazard ratio of 2.21 means that 2.21 as many times customers with fiber optic are churning than those with DSL at any given time. So that means that fiber optic has a significantly higher risk of churn than DSL. And then the next coefficient, right, this is going in the opposite direction, right? We are comparing no internet service to DSL. So the hazard ratio of 0.4 less than 1 implies that 0.4 as many customers without internet service are churning as those with DSL. So customers with no internet service have a significantly lower hazard than those hazard of churn than those. And that sort of was borne out in what we saw in those curves, right? So the survival curves, the highest survival probability was no internet service, followed by DSL, and then followed by fiber. So one of the other interesting things that we can do is we can look at that instantaneous probability of churning. So the probability of churning in that next instant. Right, and this is another way, so that's what we're looking at here. We are looking at the probability of churning in t plus 1, given that you haven't churned in time t. And so we can sort of see, this is going to be like the flip of the Kaplan-Meier curve in one way. The Kaplan-Meier curves are cumulative. This is not cumulative, but we can see that fiber optic has the highest hazard of churn, right? And that's shown in green. Followed by DSL, and then followed by no internet. And so there are little blips here. I don't see anything like highly remarkable, but there are little blips here that like, okay, maybe customers are a little bit more likely to churn right before the 24-month point. Maybe there's a story there. I don't particularly see anything terribly compelling, but what this is telling us is that instantaneous hazard. You might be saying to yourself at this point, like, okay, Andrea, that's cool. You showed me some syntax. We have talked about some interpretations, but how does it work? So that's going to be the last thing that we are going to cover today. So recall that when we started, I showed you our sort of naive estimates of survival probability. And recall that what we have to do at each point in time is we need to understand the risk set, right? So for each point in time, who is at risk of having the event? So one way that I think is helpful to think about this is if you already churned in month 3, you canceled your contract. You are not at risk to churn in month 1, right? You've already churned, you've already canceled. So you do not belong in the risk set. You're not eligible to be in the risk set. You're not eligible to be in the denominator. So you need to be removed from the risk set. And that's essentially what we are going to spend some time talking about. So we're going to estimate survival probabilities, and we're going to do so by dividing the number of customers who have survived, excluding censoring, at time t, and we're going to divide that by the number of customers who had survived by time t minus 1. And then the Kaplan-Meier estimate is simply the conditional, is the product of all those conditional probabilities. So we'll multiply all those conditional probabilities together. All right, so how are we going to do that? So we're going to play around with some R code to do that. This is a little function that I have written. This function takes 3 arguments. It takes a data frame, it takes a time variable, it takes an event marker. So the first thing that we need to do is we need to figure out how many people are eligible to be in the risk set at the start, right? So what we're going to do is I'm just going to take that data frame and I'm going to say how many rows are in that data frame, right? How many customers are in that data frame? How many observations are in that data frame? These are how many people are eligible to be in the risk set at the start. I'm assigning that to the start. The next thing that we're going to do is we're going to group by our units of time. So I'm going to say group by my unit of time, group by month, right? So, and for each month, give me a sum. Give me a sum of the people who have had the event of interest, so people who have churned, and then give me a sum of people who have been censored. So you can imagine a data frame where I'm just going to have 3 variables, right? I'm going to have month 0, month 1, month 2, and then I'm going to have the number of people who had the event or the number of people who were censored, right? So it's just going to be a group by, summarize, at total it all up for each one. Okay, so you remember how I said there are 3 lines of code we're going to talk about. These are the 3 lines of code. Right? This is essentially what I think is sort of the crux of the Kaplan-Meier. So we've been talking about what we want to do is we want to understand how many individuals are at risk at each point in time. So all we're going to do is we are going to take the total number of observations who were at risk at the start of the period, which is about 7,000. And then we are just going to create a cumulative sum of all the people who either had the event or churned, and we're just going to subtract those out, right? So that's what that line and risk with the line is doing. We're saying how many did we have at start, subtract the cumulative sum of those who have had the event, those who churned, and then subtract the cumulative sum of those who are censored. And then we are creating in the next line, the survival probability. We are calculating that probability, simple division, right? We're saying the number of individuals who were at risk, the number of individuals who are eligible to have that event of interest, minus the number of those who actually had the event, and then divided by the number who are at risk. And then the last thing that we are doing is we are taking that product. We are multiplying all of those conditional probabilities together. And that gives us our Kaplan-Meier estimate. So I'm printing one more column here for the sake of illustration, but these are our Kaplan-Meier estimates. This is the exact same thing that the survival package did, right? So essentially what we show this because I think it gets more intuitive, right? So I said we had about 7,000 observations at start, okay? So we take our 7,000 observations at start. In time 0, we have no one who had the event. We have 11 observations who are censored. 7,043 minus 11 equals next 7,032, right? And then 7,032, we are just taking the cumulative sum of those who have had the event and those who are censored. That's all we're doing. We're saying this is a risk set is this minus, this minus the cumulative sum of those who have had the event and those who have been censored. So we're just iteratively updating our risk set so that we have an appropriate denominator. And then it's just arithmetic. So that we did it. So taking a step back, what did we do? So we compared three implementations. We compared sort of the old school, the classic way of doing this, using the survival package, really, really, really valuable. Just a quick couple lines of code, really, really quick and easy to get started. We also looked at the new school, the censored package, this parsnip extension package, which is a little bit more verbose, but it's really nice to work with, in this tidy models ecosystem and have a consistent experience fitting and predicting models and, particularly the objects that you get back. And then lastly, we looked at my school. We looked at, some functions written to give you an intuition for how the math works. Please, dear God, if you go to my GitHub, like don't use that anywhere, like just use it to like understand what we're doing, but don't actually, use it anywhere. But I hope it's been helpful to give you an intuition. So let's go back to, to where we started. So where we started, we talked about how it can be really tempting. It's a very sort of common pitfall to treat censored observations as missing. But I hope that I have shown why censored observations are not missing, right? We have partial information for them, and they can contribute information for as long as they are at risk or as long as they are eligible to be in the risk set. And so therefore, it's really, really critical to think about censored observations when you have time to event data. And thankfully, we have a whole bunch of tools at our disposal provided by survival analyses to deal with censored time to event data. And then lastly, there are several R packages for implementing survival analysis. Before I wrap up, I will also throw a teaser out there that these are the like bread and butter of survival analyses. This is often like where you would start if you're trying to understand time to event data. Kaplan-Meier survival curves and Cox proportional hazards. But there's loads, you can go a lot deeper into this. So competing risks occurs when there are like multiple possible outcomes. So survival analysis, comes from that biomedical literature where we're predicting time from disease onset to death, but that's not always, it's not always, just those two outcomes, right? So you could have death from that disease, death from another cause, you could have a treatment response, you could have remission. So when there are multiple possible outcomes, you would want to look to some competing risks. You can also, there's, different classes of models for predicting events that would recur. So perhaps it's a disease that is going to like keep coming back, disease recurrence. I think about this in the context of repurchases. So something that you might repurchase at a fairly consistent interval. Another example of a special topic is interval censored data. So we talked about right censored data today. We talked about when you know something about an individual starting point, but you don't know something about their ending point. But that's not the only kind of censoring that occurs. So interval censoring data occurs when you know that something happened, you know that something occurred, but you don't know exactly when it occurred. So imagine, you can think about this like in the context of like dentistry or ophthalmology. You go in for a checkup and you know that something occurred. You don't know exactly when it was within that interval. And then the last one is kind of exciting to me. There are some R packages for simulating time to event data that look kind of fun to play around with. And before I will wrap up, because if you want to learn more, there are some really, really, really great resources out there. So Emily Zabor has this really awesome tutorial on survival analysis. She's got loads of code in there. It'd be really helpful if you want to review any of this. Hannah Frick's talk from our video conference last year is introduces that censored package. So if you wanted to learn more about that censored package, that is where I would point you, along with the package documentation. There are this Red Door Analytics has some fun tutorials, particularly about some of the more special topics that I just mentioned. There's that Cox package for simulating survival data. Oh, and we didn't talk about this. The ggsurfit package has built-in plotting functions. I tend to do everything in ggplot, but the ggsurfit package has some nice functions to just sort of really readily generate Kaplan-Meier survival curves, and some of them are nice that you can, like, print the risk table right from it. So there's loads out there on survival analysis, and loads where you can learn. Then I think that's it. Lots of questions.
I have one. How would you implement seasonality? Would that be another covariate that you would facet in?
Oh, yeah, beautiful. Okay. So I think what you're sort of saying, right, is some sort of like cohort effect, I'm guessing.
Mm-hmm.
So you have like, let me try and think of an example.
So let's say that it doesn't really matter if you've been for 4 months or 5 months. If it's December, you're probably.
Yeah. So, and is that more of a function of, yeah, I would have some sort of cohort, like I would think of encoding that as a cohort of like what you said. Oh, but you're saying like
every
yeah. Yeah.
Every December there's a higher chance.
Everything, if you were starting in January or November, it doesn't bring you many.
Yeah, I'm trying to think of
I think what you is really for initial day, but nobody is thinking stuff. Only people matters is the kind of whereas what you're bringing in, something with
Carl, if you, we can actually hear you in here if you want to unmute. You would want to just make this comment.
Sure. Yeah. So at least in the context of the, can you hear me okay?
Well, I can hear you on my computer.
I can hear you really well too.
I'm sure you can hear
Andre
me
slightly
well.
less so. So I think your audio is, yeah.
Can
I'm plugged into your
hear
audio.
this? Okay, wow. All right, people can hear it from my little computer over here, so go ahead.
Testing. So I think at least in the Cox model context, you can encode something like a month or a specific week as a covariate in there. The Cox model has, you can have like sort of what you would call sort of like time varying coefficients in there, or time varying like covariates in there,
right,
which oddly enough, right, like in a normal context, like a month of the year would not be, but because you work in relative time on these, it would be. So you could do that in the Cox model but I think Andrea's answer is right in terms of just thinking about specific cohorts and things like that in the context of just like a Kaplan-Meier kind of non-parametric method.
presented, do you have any ways to account for returning? Obviously, that would change conditional property. Do you have ways to account for that?
So then I think you'd be looking at a slightly different model, right? So you're sort of saying, so imagine, right, and you probably actually, so like imagine it's some sort of contract that you have to keep renewing. And so you have customer, you know, Fred or whoever. And so Fred signed up in January of 2021, and then Fred renewed in January of 2022, and then, but Fred didn't renew in January of 2023. Then you'd be sort of looking at a different class of models where you're predicting those sort of recurrent events. Yeah, totally doable. Can share some resources after.
Christian was.
You had a slide, and I think it was something like. Yep. Makes me think that it's just a syntactical wrapper.
Yeah, yes, you're absolutely right. Okay, you're absolutely right.
So
So
it's using the same computation.
it is using, so great. So what you're talking about right here, yes, absolutely. So, and we could actually talk so much more about this. So the engine that you're talking about right here, so this is the sensor package, right? And it's executing that same regression, that same cost regression, but it's specifying that the engine that it's going to use here is survival. And so it is wrapping around that same survival package. Yep. And you could
Look at the line right below prices.
Yep. Yes. Yes. And so
It's identical computation, it's just, it makes the syntax of the model fitting the way, well, as you said, it's more flexible, it's more similar to other options.
yes, and it's exactly correct, right? And so then if you were to if you wanted to use that like regularized regression, you would just set that engine differently to use the Glimmet package. And then it's using the Glimmet package, but you don't have to mess around with like the whole, right? You couldn't use the formula interface for Glimmet, you have to do the model matrix plumbing. So yes, that's exactly right. So yeah, that's super observant, right? So it's actually using that same underlying package.
Should you just sit there like noticing like every little?
Craig, you said pay very close attention to the photo.
Like the footnotes.
Yeah.
Well.
Anywhere, which one? No, tell me.
No, it's forward backwards.
Yeah. Yep, okay.
So you just think that.
Of this time.
Like if the hazard ratio is just.
Yes.
So does that say just?
It's absolutely correct, and that is an assumption of, right, and so you can sort of see that borne out, right, so and so like that may or may not be an assumption that is like safe for your data. So what, and I'm sorry, something again? Sean, okay. So what Sean is pointing out, right, is sort of saying like that hazard ratio is constant across time. And so you'll notice, right, so see how these curves vary together. So that is an assumption of the Cox proportional hazard, which maybe is not, exactly. Yeah. The one way that you can, yeah. Well, there are like other little bespoke things that you could do to sort of like visualize hazards differently if you did not feel like that assumption helped for your data. And I'm sure other models. Yeah.
Well, we're looking at that, and then here, and some of the other ones too. The line gets squirrely up at the right end. Is that an artifact of getting small sample size towards the end? Is it basically uncertainty?
What's happening at the end? No, so what's happening at the end, right? Okay, so you can see it right here. I don't know what's happening with fiber optic at the end. Right, but something is happening with fiber optic at the end. And I completely agree. I feel like that's like a little bit of a smell.
In this one, you haven't made that assumption you just were talking about.
Exactly, right? So in this one, and so the fact that this squirreliness that you're noting, is the same sort of idea, right? The proportional hazards are enforcing this squirreliness, right? Given the fact that those hazards have to be proportional, but really, it's just fiber optics that is causing them. So I mean, it's totally interesting. Like, I wonder, maybe I'll play around with this, like what's going on with fiber optic at the very end. But that is what is forcing that sort of like kink in the hazards.
They signed up for a 5-year locked-in rate. And it expired.
Oh. Do you get 5-year rates for internet?
I know somebody that signed 5-year locked-in rate for fiber optic, I swear.
Really?
So I think I understood the map as, why eliminating data. My intuition said eliminating the censored data will underestimate your travel time because you're getting rid of something that could have never churned or died. So give it, so my intuitive sense was wrong. You know, an explanation.
So I think that this will help. That's why I showed that declare code, because I feel like I have the same intuition, right? So, okay. So I think what your point is, right? So in our naive estimates, our denominator is always the total at start. So our denominator is always the 7,032 observations that we started with, right? So you would think to yourself, okay, right, intuitively, if I am lowering my denominator, right, then my survival estimates, like this should not overestimate the survival probability, right? Because if I'm lowering my denominator, right, I'm lowering the risk.
I just turned it because I think my microphone is the one that's recording.
Oh, okay. But our naive estimate is 1 minus, right? So does that make sense? It's 1 minus, so I completely share that intuition. And I think the reason, that doesn't sort of intuitively make sense is because our naive estimate is 1 minus the running total divided by the. Does that sort of make sense? I know, like, yeah, no, but I feel you. I feel what you're saying.
The question that I read.
Oh, okay. It would be on the time varying in that context. Okay. But was this to a previous?
That was a previous question. That was
Oh.
one. Then he asked it.
Oh, okay.
All right, sorry.
No, you're good. You're good. Yeah.
I'm not a data scientist, but let's say that I'm gonna see picture. What kind of questions to say, okay, then let's put a note that one is. As you can see, it's quite so nice that anyway they want to. If I'm the
Uh-huh.
new novels in this model.
Okay, so first to sort of get to, couple of points. So if I'm having a conversation with a sort of CEO about this model, I would tailor that conversation very different sort of than the conversation that I've had today, right? So I kind of came in being like, okay, I'm going to talk to, it's an academic town, and we're talking to fellow data scientists. We're going to show some code. We're going to do a little bit of math. We're going to have fun, right? I would sort of cater a conversation with the CEO very sort of differently than I would have this conversation. So I would probably, as a data scientist, I would also take it as my responsibility to workshop that language and to use simpler terms. I wouldn't necessarily, I don't even know that I would use the word hazard to talk to somebody, to a member of the C-suite. I would try to come up with more intuitive language. So that's like my side of the conversation. But your question was really about sort of like the CEO side of the conversation. So one thing that I would be thinking about, you were saying, am I going to lose my shirt on this, right? So the first thing that I would start thinking about is, well, how are you going to evaluate this model, right? You're making predictions, but how are we going to evaluate those predictions? How are we going to compare those predictions to what actually happens? So the first thing that I would recommend is to sort of think about like, what kind of monitoring or evaluation framework are we going to have in place to sort of compare, hey, the model predicts this, but this is what, but that is what actually happened. So I would sort of start thinking about an evaluation framework, other things. I would, the choice of the model, I think, goes back to conversations with domain experts, right? Like I may have some, or data scientists may have guidance in terms of best practice and the type of model, but really stakeholders have more of an intuitive sense of maybe the factors that are really important to go into that model, the variables that need to go into that model. I'm thinking about things like, yeah, so I guess I'm trying to answer your question from multiple sides. Like A, I think the data scientist has a responsibility in that conversation. B, I would encourage stakeholders to think about, how are we going to evaluate this? And then C, I would think about it as like a reciprocal back and forth conversation between data scientists and stakeholders to really sort of like, it's my job to ask a whole bunch of questions and extract that knowledge from the domain experts, who may not be the CEO, but. Yeah.
Yeah, so as a business decision maker, I would be all kinds of curious about the cohort.
Yeah.
We all live in the same market. They all have the same alternatives at the same price point. Things like that. I'd be very curious about the.
Yeah. So, and there's loads more in this data. And like I said, I will share the link to my GitHub. I pulled this from Kaggle, but there's like loads of other data in there. And the cohort effects is often like pretty important, right? So maybe, so you can imagine, so COVID is like an awesome example of a cohort effect. Like, do you think that people would behave differently, in 2019 than they do in 2022? Probably.
How embarrassing is it if our coders still use the old type?
Oh. So, no.
I've asked for-
No. I switched over the native pipe and then I was like, so I'll confess it's fine. I switched over the native pipe and then I was like in some old code base. I like went back and forth a little bit, is my point. But I switched over to the native. Yeah.
Okay.
No, I don't think it's embarrassing. No,
Okay,
joke.
well,
I
that's
don't
very
think,
helpful.
no, no, I don't think it's.
Who uses old pipe versus who uses new pipe? I think I just Googled it. I was like, what the hell? I know it was like, it used to be new, the Magritte one or whatever, but so this is like a year and a half or something, or?
A year-ish, that's the
year.
native pipe, right? So you don't need to import dplyr.
Right, which is nice.
There's some, a native archive, right?
That's
So
what
there,
that little thing, I was
Mhm.
like, what are those?
there are some minor differences.
You don't have to like do the thing where you set, if you're like adding a new variable to a data frame, before you had to like point it at itself to say, I want to save this new version as the old one. And I don't think you have to do that.
There's no side effects. It does have a side effect.
You mean you don't have to assign it?
Yeah.
I'm not.
Yeah.
No, no, but, and I ran into a fun hiccup with the native pipe, actually, but there are minor differences.
Yeah.
By side effect.
There used to be two pipes of pipe that changed the data set in place.
Oh, yes. And it looks a little funnier. Yeah.
They all look
I don't
fun.
remember the name of that operator, but yes, yeah. So you're saying you don't have to, right? You don't have to assign it, change it in place, yeah.
Anybody else have any questions? questions or? So, oh,
I'm just curious, how do you frame
So recidivism, yeah, I don't know. So recidivism seems ethically a little bit thorny to me. So that would be my like my first instinct. Is there any, I mean, I mean, from a technical perspective, I think yes, it is possible, because you have, if you're predicting time to whatever, you have some variables where you're sort of saying, I've observed this for some, I have not observed this for others. But I would want to think sort of about, right, when we're predicting things like, policing, is very, very, very ethically challenging, because of the sort of like circular nature of things, right? So we predict policing, we have more policing, we have more arrests, right? I'd probably be thinking about wondering about recidivism in this context, but I do think it's technically sort of like an appropriate thing. Yeah.
Because at least that outputs the coefficients versus something that's more non-explainable model is probably why it's used.
if we could end there and just, socialize. It's 7. Was that?
Greg's leading it.
I feel like I was forcing things. It sort of felt like the questioning was sort of tapering down a little bit. And then there's kind of a point where people can ask each other questions or talk more informally.
That was great.
Yeah, it was great talking.
Thank you.
Yeah.
Thank you.
All right, turn off the recording so we can start sweating.
Okay.
So what? Oh, and so if anybody wants to make a donation, you're more than welcome. And I've got, hold on, I have a Venmo screen here. If anybody wants to donate, and then Polly, we trust Polly to take the cash. She takes cash. So what, did you just stop it recording? Oh, no, there, you stopped sharing. There's the button.